Hey, what's up, guys? Welcome back to another video lecture from Smart Interviews. So, today we are going to discuss the LeetCode Contest 398. I'm Sanjay Kumar. Let us begin with the contest. Okay, let us start with the first problem, special array 1. An array is considered special if every pair of its adjacent elements contain two numbers with different parity. So, parity actually indicates either the number is even or odd. Yeah. So you're given an integer array nums. You're supposed to return true if nums is a special array or else false. Once again, dealing with the special array, an array is considered special if it follows this condition saying that every pair of its adjacent elements should contain two numbers. Obviously, it contains two numbers with different parity. Different parity. Yeah. So every pair, not all the pairs, every pair with adjacent elements should have different parity. Yes. If we start with the first example, nums is having only one element, that is one. You're going to return true because no adjacent elements to compare whether having different parity or not. You're going to return true. Yes. Going to the second example, 2, 1, and 4. So 2, 1, and 4. So if you see here, 2 is even, 1 is odd, and once again 4 is even. So if you compare like adjacent pairs, this is one adjacent pair and this is one other adjacent pair. So for this first adjacent pair, both the elements are having different parity. Yes, you're going to say yes, this pair is having different parity. In the second pair, both elements are having different parity, and for this pair you're going to say yes, the pairs are having different parity. So when all these pairs are having different parity, what you're supposed to do, you're going to say the entire array is a special array. Yes, that means this nums is a special one. So for this, you're going to return true. Yeah. Moving to the next example, 4, 3, 1, 6. 4, 3, 1, and 6. So for this example, 4, 3, 1, and 6. So 4 is even, odd. Here itself we got a pair that is an adjacent pair with same parity. So when we got a pair with same parity, the entire array is not at all a special array. Then from there and there itself, we can simply return false. So we got false here. The same explanation was given. Nums of 1 and nums of 2 are both odd. Nums of 1 and as well as nums of 2, if you take 0, 1, 2, 3, nums of 1 as well as nums of 2 are both odd. So answer is false. Going to the constraints. Nums dot length is less than or equals to 100 and nums of I is always less than or equals to 100. Yeah. So what is the logic? What is the logic for this? So that we are going to say whether the array is special or not. What could be the logic? Very simple, in very simple sense. Do we need to compare all the pairs? Do we need to check all the pairs whether they have a same parity or different parity? Yes. So first thing first, we are supposed to check whether all the pairs are having same or different parity. So let us first write the logic for this. The first thing, check all the pairs, all adjacent pairs. What we are supposed to check? Parity. Parity. Yes. So what if they are having same parity? What if they're having same parity at any point of time? Yes, we're supposed to return false. Yes. After completion of the entire array, that means all checking the condition for all the pairs is done. That means each and every pair is having a different parity. Now what can we say after completion of all the entire logic? Yes, we can simply return because the entire array is a special array. Yes. And what is the complexity if you want to implement this kind of logic? Yes, as I said, we need to check all the adjacent pairs, that means we need to firstly figure out how many pairs do we have. Yes. And after figuring out, we need to check like how much time does this comparison takes to check whether the parity is same or not. Yes. So this actually depends the complexity. So firstly, how many pairs does it actually exist? If array is of length 3, only two pairs existed. This is one pair and this is one other pair. Yes. In the same manner, if array is of length 4, we can simply say this is one pair, this is one other pair, this is the third pair. So length for 3 pairs. In general, if it is of length n, we are having n minus 1 pairs. So that means, do we need to get all the n minus 1 pairs? Yes. So if you want to get all the n minus 1 pairs, and after getting all these n minus 1 pairs, we are supposed to check whether they are having same parity or not. Yes. How could we check whether they are having same parity? How could we check? So firstly, to check whether the number is even or odd, we are going to simply apply mod 2. Yes. And after applying mod 2, we are having only two possibilities. Either it could be even or odd. So if it is even, we are going to get the remainder as 0 or else remainder as 1. We can simply say it is even, this is odd. Yeah. So as I said, proceeding according to the logic, we need to simply iterate for n minus 1 times. So can I just simply start iterating either from 1 or else either from 0 until n minus 1 times? So can I just simply say, let us say a for loop I starting from 0 to n minus 1, this is exclusive, or else if I can simply start from 1, if I can simply start from 1 to n minus 1, and this is inclusive. I'm just specifying something of this format, 1 to n minus 1, n minus 1. So in this process, I need to get each and every pair of adjacent elements. How could I get the first pair? The first pair is of 0 and 1. My I is starting from 1. I'm going to get the first pair as nums of I minus 1, because the first element of the first pair is going to be the 0, nums of 0. And the second element of the first pair is going to be nums of I, that is nums of 1. Nums of I. How could I check the parity? As I already discussed, mod 2, if that is 0, you're going to say even or else 1. You're going to apply mod 2 here, mod 2. After getting this is having only two possibilities, either 0 or else 1. Yes, if both are even, we're going to get this as 0 as well as this as 0. If both are odd, you're going to get this as 1 as well as this as 1. So if I can simply compare these two, saying that if both are having same value after applying the mod with 2, if both are having same value, can I just simply return false from there itself, because they're having same parity. Adding a condition for this, if nums of I minus 1 mod 2, if that is equals to nums of I mod 2, you're going to say return false. Yes, after completion of this checking process for all the entire n minus 1 pairs, if any of the pair doesn't satisfy this condition, saying that nums of I minus 1 mod 2, if that is equals to nums of I mod 2, you're going to return true. Yes, because the entire array is being satisfied. So return true. Yeah. So finally you're going to return true if any of these doesn't encounter this loop. Yeah, I hope that is clear for everyone. And as I said, we need n minus 1 iterations. Yes, n minus 1 iterations, and this process is taking constant time. This checking process is taking constant time. So can I just simply say the overall complexity of this entire logic is big O of n? Yes, let me write it here. The logic that we have discussed is having big O of n and constant extra space. Moving back to the next problem, special arrays 2. So this problem is an extension to the previous problem. Along with an integer nums, you're also given a 2D matrix, that is queries. This queries actually indicates two numbers, starting index as well as ending index. And your task is to supposed to say whether the subarray from starting index to ending index of the nums is special or not. Finally, you're supposed to return a Boolean answer, that is an array, where array of I actually indicates whether the particular query is a special array or not. Yes, I hope the problem statement is clear. Yes, so based on this problem statement, the very general solution that comes into everyone's mind is, what if you can simply reuse the previous problem function, that is special array 1, for each and every query? What if you can simply use the special array 1 function? Yes, obviously we can, and we can simply populate this array and we can simply return this Boolean answer finally. Yes, and if you want to implement this process, what is the complexity that is going to be? you're going to perform this operation for each and every query, and the special array1 function actually takes n time. But if you try to look at the constraints, nums of I can go maximum up to 10 power 5, and queries also can go maximum up to 10 power 5, as well as nums length also can go up to maximum of 10 power 5. So considering these two, this q into n solution will be 10 power 10, which is actually practically not possible. So obviously we're supposed to think of a optimized solution. Yes. So when there is an optimized solution, when there comes to the optimized solution, the first thing that we can think is we need to firstly check if there exists a single pair which has the same parity from the starting index to the ending index. Can we just simply say the entire array is not special? Yes, obviously true. Yes. That means our task is simplified, something like if you can somehow figure out at least a single pair that is present in between the starting and ending index, in between the starting and ending index. If there exists at least a single pair, we can simply return false. Making sense? Yes. So let us make the way forward in getting at least a one pair in the range of a comma b. So at least a pair with same parity in, let us say, instead of from to, it is difficult, let us maintain it as a comma b for better sense. At least a pair with same parity in, let us say, nums of a comma b. I hope that is making sense. If we can somehow figure out at least a pair with same parity in nums of a comma b, we can simply return false, or else we can simply populate answer array with false. Yes, finally, after completing the entire process, if we do not find any pair, if we do not find any pair, we can simply return, or else we can simply add true to our answer. True. Yes. So this is one of the logic. So if you want to implement this logic, we should firstly find whether there exists a pair. Yes. How could we find whether there exists a pair in between the range a comma b? How could we find this? Yes. So instead of performing this for each and every query, what if we can simply perform the entire, like what if we can simply get all the pair indices which are having same parity in the entire array. By constructing this entire array, what if we can simply perform like checking whether there exists a pair in this entire array? That actually helps us, right? Yes. Let us start figuring out building how can we populate an array. Let us say parity array, same parity array. Let us say we are going to populate same parity, or else parity array. Array. So instead of storing starting index as well as ending index of each and every parity, what if you can simply store the starting index of a pair of the parity? Yes, like of the particular adjacent pair. That actually helps us, right? So let me indicate here this parity array. Parity array actually stores what it actually stores: starting index idx of the adjacent pair. So what I'm saying is it actually stores the starting index of the adjacent pair. Instead of storing both the elements, both the indices, we can simply store the starting index of the adjacent pair. That actually helps us without storing everything as required. Okay. Okay. Let us try to implement this logic on an array. Let us take the second example. 4316. Okay. 4316. Let us go with indices 0, 1, 2, 3. So this is even, odd, even. Yes. So as I said, the parity array So I'm going to populate this parity array, which actually looks something like this. Yes. So starting from the 0th index, so like starting from 0th or first index. Okay, let us start from the first index. Okay. If I'm starting from the first index, what is the first pair that I'm supposed to consider? 0 and 1, right? 0 and 1. So if I want to consider 0 and 1, so this is the pair that I'm going to consider. So for this adjacent pair, do we have different parity or same parity? We do have different parity. So start moving ahead. Yes. So for this pair, do we have different parity or same parity? We have same parity. As I said, when we are having same parity to the adjacent pair, what we're supposed to store? We can simply store the starting index. Okay. I'm storing the starting index, that is 1. Okay. Moving forward, moving forward. Now I'm considering this pair. So for this pair, do we have same parity or different parity for this adjacent pair? We do have different parity. Do we need to include in our parity array? No, we do not. So finally, this is our parity array. Yes. So that means we are going to iterate to the entire array once and populate an array that is parity array, which actually stores the starting index of each and every adjacent pair which has same parity. Yes. Now let us deal with the queries. Let us take the queries 0, 2 and 0. Sorry, 0, 2 and 2, 3. The query says 0, 2 as well as 2, 3. 2, 3. So this is query 1 and this is query 2. Yeah, let us deal about first query and later on second query. So the first query says I want to check whether the subarray starting from 0th index to second index is special or not. Yes, so this actually indicates this part of subarray. Let me take the subarray out. 4 3 1. Now manually check, is this a special array? Yes, this is a special array. We do have two, like an adjacent pair with same parity, two elements with same parity, which is an adjacent pair. So we can simply say this is not a special array. Yes, but based on the parity array populated, how can we just simply get, like, can we just simply get this is not a special array? Yes. Okay. So as I said, query one AB. Let me name it AB. A, B. This is 0 and 2. Yes, if I can somehow get an element which is between A comma B in the parity array, that actually helps us to just simply add false into my answer array. Yes, yes. So if you see here, A is present, that is 0, and B is present, that is 2. If I can simply get the element that is between A comma B, how could I get this? How could I get this? Yeah, one more thing. When I'm trying to populate this parity array, this example is being very small, but when I'm trying to populate this parity array, let us say one other element is also present here. Let us say that is 8. So if the element is 8, once again this is even. So what element that you're going to add into this parity array? Yes, that is going to be 3, right? Yeah, the starting index. So that means if you see here, this array is by default sorted, because while you're traversing itself, if parity of two elements that are adjacent as well as they are same, you're going to add it to the parity array. So by default it is sorted. So as this is a sorted array, that is, as this is a parity array is sorted, as I want an element between A comma B, can I just simply use binary search? Yes, in more specific, binary search seal on binary search floor. Making sense, right? Yeah. For A, I need to get the largest element, which is which is just greater than A. Yes. Can I just simply call binary search seal on A? Yes. So for A, I'm going to call binary search seal. That means I need the largest element which is just larger than A. Yes, making sense. In the same manner, for B, I need to calculate some value that is smaller than B. If I want to calculate a value that is smaller than B, can I just simply say that is binary search floor? Binary search floor, that is a smaller element, just smaller than B, or else, yeah, just smaller than B. So we can simply say binary search seal and binary search floor. If I can simply calculate binary search seal on A on this entire parity array, binary search floor on this B on this entire parity array, if I can somehow get a value, if that is in the range of A comma B, I can simply add false into my answer array. Yes, yeah. So if you see here, this is 0 and 2. If I can simply get binary search seal on 0, I'm going to get 1 here. binary search seal this is, and if I can simply get binary search floor of 2, I'm going to get once again 1. So can I just simply say this 1 is in the range of 0 and 2? That means this array is not special because there exists a pair that is adjacent as well as having same parity. Making sense, right? Yeah. So with this, I can simply add false into my answer array. Let us also deal about the second query. So second query is something like Q2 is starting from 2 to 3. Something like 2 to 3. Yeah. Apply binary search seal for 2 in the parity array. Do we have any element? Yes, we do have an element that is 3. Apply binary search floor on this, like, oh sorry, I have added an element and I have removed it. Yeah. So this is going to the parity array data. Yeah. So apply binary search floor on the number 3. So when I apply binary search floor on the number 3, I'm going to get 1. Yes. So for 2, I'm not going to get anything. For 3, I'm going to get 1. Yes. So with this, what conclusion are you going to make? What conclusion are you going to make? Obviously the element that is present is smaller than the value that is smaller value of a comma b. Yes, if that is smaller of a comma b, that means the value is not all in the range of a comma b. Now can you say there exists a pair with, like, with adjacent with having same parity? No, right? That means as we are not having any pair, can I just simply add true to my answer? Yes. So this is one of the conclusion. Making sense, right? Yeah. So let us make the logic more clear. Let us go to the logic once again. Let us make the logic more clear. So first thing, what we did, we have tried to populate parity array. The first thing, populate parity array. As I already discussed, this parity array actually stores the starting index of a page which is adjacent as well as having same parity. Yes. So try to populate parity array. Everyone knows how to populate this. And the next step after populating this parity array, what I'm supposed to do, go through each and every query. For each query, what I'm supposed to do, on A, I need to apply binary search seal. On B, I need to apply binary search floor. Okay, let me try to store these values. Let us say P, Q. Okay, I got two values. Let's say P and Q. If seal is not present for A, I'm going to return -1. If floor is not present for Q, I'm going to return -1, or else null. Anything will be fine, or null. Anything will be fine. Yeah. So if this binary search A that actually gives you P as well as Q, binary search on floor that actually gives you Q, what I'm supposed to do, if this PQ should be in the range of A comma, yes, making sense, right? This P and Q should be in the range of A comma P. So P comma Q should belongs to A comma B. And one more thing, so if I try to include B, if there exists an element which is equal to B, do you need to consider that? Yes, because as we're storing the first index, as we're storing the starting index of the pair, actually we do not require to consider this. So can I just simply say this belongs to the range of A comma B? If this belongs to the range of A comma B, what I'm supposed to do? Simply add false to my answer. Yes. But what if that doesn't exist? What if that doesn't exist? Else, just add true to my answer. Yes. I hope that is making sense for everyone. Yes. And if you see here, trying to populate a parity array, it takes n time to traverse to populate the parity array, as well as we need to populate an array. As we're trying to populate an array, at max it may take n-1 space, because what if every element is something like odd, even, odd, even, odd, even? So obviously n-1 space will be entered into the parity array. So n-1 space will be there. In general, can we just simply consider n space? So populating this parity array actually takes n time as well as n space. And for each query, that means for each query Q, we're trying to apply binary search. Yes, binary search. And this is going to take 2 times of log n. We can simplify to say log n time with base 2. Yes, And if this is belongs, this is a constant time operation, and you're going to return true or else false. This is a constant time operation. Yes. And with this, the overall complexity goes to be, let me move it to bit top. Second one, the complexity that we have discussed is n plus, sorry, n plus q times of log n base 2 comma n extra space. Yes, so we are trying to populate a parity array which is actually taking n space and n time to populate this, as well as for each and every query you're trying to apply binary search seed and flow, which is going to be the complexity of q times of log. I hope that is clear for everyone. Yes, if you see here, even though we are using n extra space, but the complexity is n plus q times of log n. We are supposed to even reduce this. Okay, let us discuss that. Let us take an example. 4316 4316 0 1 2 3, and the queries are, let us say, q1 as well as q2. I hope the first one is from 0 to 2 and second one is from 2 to 3. Yeah, 0 to 2 and 2 to 3. Okay, so instead of populating an array something of the previous format, what if you can simply populate an array which is actually storing the count of prefix parity of adjacent pairs, and this parity actually indicates opposite parity. Count of prefix opposite parity of adjacent pairs. Let me write different parity or else. Let us define an extra array saying that which actually stores count of prefix different parity of adjacent pairs. Yes, okay, so maybe the statement is not making much sense. Let us discuss with this example. So this parity, which array that I'm going to populate, will actually help something in this format. So firstly at zeroth index, when someone asks you, when there is only one element in the array and ask you like, is this a super array or not? Is this a special array or not? What do you say? Obviously, this is a special array. So if it want to be a special array, what if you can simply take one here, saying that if there exists only one element, that is the starting element, I'm going to say this is also a special array. Yes. In the same manner, going to the first, second, and third. Yes. Try to extend this prefix parity. So this is even, odd, even. Yeah, so these two are having different parity. So as they're having different parity, what can I just simply extend my prefix parity, something like parity of I is going to be, as I said, prefix parity of I minus 1 plus 1. Yes, if it has a different parity. Okay, maybe this array is not making much sense because parity is the same name. Let us name it prefix parity instead. Prefix parity, let us say pp instead of prefix parity, this entire thing. I'm just simply calling pp of I is going to be pp of I minus 1 plus 1 if it is having different parity. Yes, so obviously these two are having different parity. So what I'm going to do, I'm going to increase the count of parity here to 2. Yes, start comparing these two are having same parity, the count remains same. Start comparing these two are having different parity, the parity has increased to 3. Yes, now let us try to answer queries. Okay, let me take this parity prefix parity array to the bottom. That is 1 2 2 3. We got 1 2 2 3, or else let us move it aside. Here. Okay, as we're already having this prefix parity, with the help of this prefix parity, sorry, this is the prefix parity. With the help of this, we are going to say whether this particular subarray is a super array or not. Yes, a special array or not. So 0 to 2. So 0 to 2, if it should be a special array, that means none of the adjacent pairs should have same parity. So obviously, if none of the adjacent pair is having same parity, obviously the count should be increased. Like count should be, what is going to be the count here until the last index? As I'm saying, query 1 is starting from 0th index to 2nd index. 0th index to 2nd index. From 0th index to 2nd index, if you can simply get the prefix parity count, that is going to be pp of q1 of 1 minus pp of q1 of 0. So what do we get from this? From 2 to 0, what is the count? From 2 to 0, 2 minus 1, that is going to be 1. But as this is a prefix, like as this is a query from 0 to 2, so if it is from 0 1 2 0 to 2, obviously two pairs should exist, right? This is one pair and this is one other pair, but we got only one pair which is having different parity. That means one other pair actually exists which is having same parity. So can I just simply add false for this condition into my answer array? Yes, making sense, right? Yes. In the same manner, start getting prefix parity values, the count of prefix parity values from 2 to 3. That means you're going to say pp of 3 minus pp of 2. What do we get from this? That is going to be 3 minus 2, that is going to be 1. And if you also try to get the indices from 2 to 3, only one parity, like one adjacent pair exists, and this one adjacent pair is the adjacent pair which is having different parity. So with this, I'm just going to say just the entire subarray from 2 to 3 is a special array. So I'm going to say simply say this as add true to my answer. I hope that is making sense. And with this, what is the complexity compared to the previous? Firstly, what all things we actually did? What all things we actually did? We tried to populate prefix parity. Yes, populate prefix parity. Yes, and after populating this prefix parity, we are trying to iterate on queries for each query. What we're supposed to do? We're supposed to get prefix parity. Let us say this is pp, prefix parity of q. Let us say this is ith query, qi of 1 minus prefix parity of qi of 0. What if this value is, if I try to compare with this value, if this value is larger than compared to this value, we are going to return, right? Return false, or else add false. What if this value is smaller than q of I of 1 minus q of I of 0? What I'm supposed to do here with this condition? If this is smaller than this, I'm going to simply add false. Yes. What if this condition is true? What if this condition is satisfied? Like that means this condition is not satisfied. I'm going to add true to my answer. And finally, I'm going to return this. I hope that is clear. So if I try to discuss the complexity for this logic, this populating this prefix parity is taking n time, as well as we are trying to populate this prefix parity, and this is for sure an extra space. Yes. And what about for each query? And for each query, we are trying to get prefix parity of q of I of 1 minus q of I of 0. And if it is less than q of I of 1 minus q of I of 0, what we are going to do? We are going to add false, or else we are going to add true. And how much does it actually going to take? Yes. And this is actually going to take constant time. So with this, the overall complexity of this third solution that we have discussed is slightly optimized to the compared to the previous one, that is n plus q comma n extra space. I hope that is clear. Moving to the next problem. Sum of digit difference of all pairs. You're given an array nums consisting of positive integers where all integers have same number of digits. Same number of digits. The digit difference between two integers is count of count of different digits that are present in same position. At same position, if the count of different digit is present, we are going to increment the count. Yes, and return the sum of digit differences between all the pairs of the nums. Yes, so compared to the previous one, this is not just adjacent pairs. We are just trying to get all the pairs. Yes, all the pairs. So if you see here, 13 and 23. So for 13, if you go with position 0, we have 1 in its position 0, and for 23 we have 2 in its position 0. So can I just simply say difference is 1 here? Yes. And moving forward to the position 1, we have 3 in position for 1 for 13, and we have 3 in position 1 for 23. And once again this count remains as it is. So this is the way you're going to count. Yes. And if you want to implement this in a very brute force manner, we're going to perform this operation for all the pairs. So in general, n square pairs exist, and for each and every pair we are supposed to iterate for number of digits present that are present. Yes, so it is going to be n square times number of digits that are present. Yes, can we do anything else to optimize this? Yes, if you look at this particular array, the approach is really straightforward. So if you see here, 13 and 23, 13 and 23, 13 and 12 are giving you two pairs. Yes, 13 and 23 as well as 13 and 12. So if you see here, for these two pairs, I'm just considering 13 as a multiple. See, 13 with 23 as well as 13 with 12. Yeah, so I'm getting two here, two pairs. So with what I'm going to say, I'm having two pairs which is having different digit count. Yes, so can I just simply go in this manner? Yes, instead of performing in performing getting the digit difference for each and every pair, what if we can simply get the count of each and every bit that is present? So if you see here, the entire each and every digit is of two digit. Yes, two digit. Let us say this is digit zeroth position, this is first position, and for each and every position, what all possibilities do we have? Either it could be 0, either it could be 1, or so on so on, either it could be 9. Yes, only these possibilities exist. Only these possibilities exist. For all these possibilities, if we can somehow get the count of number of 0 or count of number of 1 or else count of number of 2 until count of number of 9 in its particular position, does it actually help us? Let us see. So if you see here, 13, 13, 23 and 12. Yes, 13, 23 and 12. So 13 can make a pair with 23 as well as 12 can make a pair with 23. So with these two pairs, instead of saying in this manner, what if I can simply say two digits actually exist, two digits, that is 0 and 1, 0th position and first position, and for each and every bit we have all these possibilities, something like either it could be 0, either it could be 1, either it could be 2, 3, 4, 5, 6, 7, 8, 9. Yes, for each and every bit, either these values are possible for each and every position. So if we see 13 at 0th position we have 1. So can I just simply go to 1 and increment its count? Let us say everything is initialized with 0 in the very start, so this will be going to be 1. And for 23, 2 is at 0th position, and for 12 1 is at second first zeroth position. So can I just simply increment it by 1? Yes. In the same manner, going for the first position, 3 is present for 13, go to, yes, this is going to be 3. 3 is once again present for 23, and this is going to be 2 now. 2 is present for 12, and this is going to be 1 now. So instead of this, yes, and the entire remaining will be zeros. Yeah. So with this, with the help of this particular, let us say some kind of matrix, with the help of this kind of matrix, can we just simply get our answer? What else we are required? Yes. So as I said, what if we can simply get answer plus equals to count of number of, this actually indicates count of number of I at that particular position. Yes, count of number of digit I at position, either it could be 0 or else one first position. Yes. So can I just simply do something like this? We have two ones at 0th position, two ones at 0th position, and if I are having two ones at 0th position, and if I want to make pair with others such that which do not have a 1 at 0th position, how many pairs does it actually makes? Yes, if you're having 2 here, the remaining numbers which with which it can make pair is going to be n minus the remaining which is not having 2. Yes. So can I just simply say, if you are having 2 here, the remaining is going to be 3 minus 2, that is going to be 1. So that is going to be 3 minus 2 in total, that is going to be 2 into 1 is going to be 2. So two pairs which are possible, which are starting like at 0th position, which are starting with 1. In the same manner, go for this. This is done. Go for this. So we are having 2 1 2 in 0th position. We are having 1 2 in 0th position. So if you are having 1 2 in 0th position, how many 2's we do not have in 0th position? Yes, 3 minus 2, right? 3 minus, sorry, 3 minus 1 2's. 3 minus 1. So this is going to be 1 into 2. So once again, two pairs which are possible. And once again going to this. Yeah, we can simply perform the same operation for all of this. So it is going to be 0 times of 3 minus 0. Once again, it is going to be 0. Because it is going to be 0, I'm not going just considering it. Yeah, going to this. This actually says there is 1 2 in first position. Yes, 1 2 count of this is going to be 1 1 2 in first position. So if there is 1 2, how many number of 2's that do not have in first position? 3 minus 1, right? So it is going to be 1 into 2, once again going to be 2. In the same manner, what about this? So this is going to say we are having two threes at first position. So if you are having two threes, number of non threes at first position are going to be 3 minus 2, that is going to be 2 into 1 is going to be 2. So we got 2 4 6 8. So in total we got 8 pairs, which is actually giving you count is going to be 8. But in general, what we are required only 4. But if you see here, what all pairs we are actually making, as I said in the previous way, as I said in the previous, for 13 we can make pair with 23 and say 13 and 23 is a pair, and once again with 23 we can make a pair with 13 and say 23 and 13 is one more pair. Yes. So if you see here, these are two pairs but both are same, but we are required to count this only once. So in the same manner, we got all different pairs which are also included in the same. So overall it is going to be number that we got by 2, because each and every pair is counted twice. So answer is going to be, the final answer that you are going to return is going to be answer by 2. So this is going to be the final answer. I hope the logic is clear. Let us try to frame it in the statements. Yeah, so what it actually we do, firstly we try to populate this some kind of matrix. Let us say digit count matrix. Let us say this is digit count. Yes, the first thing that we did is populate digit count. So we try to populate digit count. And what is the next step after populating digit count? We're trying to iterate on this digit count and try to check, like trying to increment the count based on number of digits in the particular position multiplied with number of non digits in that particular position. Yes, traverse on the, let's say this is matrix, traverse on the matrix, increment count, and finally what is the result that you're going to return? Return answer by 2. Increment answer it is. And how you're going to increment this answer? This answer, it is going to be plus equals to count of digit multiply with count of, let us say this is this particular digit, count of that particular digit multiply with count of non-digit. Yes, and this is going to be you're going to get from digit count, and this is something like n minus digit count. I hope this is clear. And finally, you're going to return answer that is going to be answer by 2 because we are going to add each and everything twice. And if you try to look at the complexity, how much does it actually takes to populate this digit count matrix? Yes, you're supposed to iterate on the entire nums array, which actually takes n time. And for each and every number, what you're supposed to do, you're supposed to iterate on all the digits of the particular number, which actually takes number of digits length. In general, if it can simply take some value k, it is going to be n into k. Then after, for each and every time at the particular bit, you're going to go you're going to the count array and increment the count. Yes, that is constant. And traversing on this matrix, as it also take n into k time, and as well as you're going to increment your answer, that is going to be the constant time. I hope the logic is clear. The second solution that we got, this is first one, and second one, instead of number of digits, if we can simply assume number of digits, if this is equals to k, we can say m square into k, and second solution is n into k. 2 times of n into k, we can generalize to say n into k is the complexity for the second solution. I hope the solution is clear. Thanks for watching. Let us meet once again back